As we know, Revit is essentially just a large database, and all of our families carry parameters which carry information, which can be used for a myriad of things, whether it's to drive geometry or populate a schedule. So I'm going to show you some ways that we can use these parameters along with formulas and pull out data and use that data. So with family creation, which is probably the most important part, geometry is irrelevant as far as pushing data goes. It's not to say it's not important. It's just if we're going to schedule something, we want to be able to use that data. The other key thing is do not overmodel. Overmodeling, if you're, say, using something many times within a project, maybe it's a light fixture. You don't want to model all the little fins in the louver. That just bloats your model and makes it pretty difficult to use. So when we're creating our families, we need to consider where the information comes from, where it's going, what's it going to do when it gets there, and how can we use that information. Another important aspect of our families are the connectors. This is how we push our information from one family to another or into a schedule. And when we have our connectors, we need to associate all the available parameters in the connector and link them to an appropriate parameter within the family itself. Now, when we're talking about HVAC and plumbing, important things to consider are the flow configurations, and we can have a calculated value which uses the information being pushed to the connector from another family. This is typically through a physical connection, or it could be a logical connection as well. The system allows the connector to read all that data even if it's not connected. Preset is used to push the information from your family into another family, and we'll be demonstrating that. Another important one is flow direction. Is it in or out? Now, supply air terminals blow air out, but the connector sees that information as being air supplied in to the family. Return air terminals, conversely, send it out or back into the ductwork. System classification is, we always want to try and define these so that we can utilize the information appropriately. We use global, rarely, or at least my personal opinion is using it pretty rarely. If you have, say, a valve, then that will pick up the system classification to whatever system type it's being put into, whether it be hydronic supply or hydronic return. It will report those. Now, we want to simplify and get on with designing by using formulas and lookup tables so that a lot of the heavy lifting is done by our families themselves. Now, we know what our formulas are. They're industry standard formulas. So we can utilize these to push information from one parameter into another parameter, calculate it, and give us an expected outcome. The reason I advocate this is so that we don't make errors, or if we do, we're really limiting them. You're not accidentally pushing the wrong button on a calculator or something that's going to cause an error further down the road and potentially cost us money. So if we can put all of that into our families, then we can get all of this information accurately calculated. And I'll show you what I mean here in just a little bit. The use of lookup tables is important because we all get catalogs from our manufacturers, and we can use those tables within the manufacturer's catalog to generate proper values within our families themselves. So if we took a quick look at, let's say, an air terminal, and I'll just open this guy up for some editing. Here we've got our air terminal with our connector set to preset. Flow direction is in, and system classification is supply air. And you can see I have my pressure drop being associated to a family parameter, and I have my flow also being associated to a family parameter. And then I also have the neck size on that air terminal associated to a dimensional parameter within the family. Now if we take a look at our parameters, we can see we've got a design air terminal neck velocity, and we can utilize that to drive information from a lookup table and set up a formula that'll then populate the lookup table based upon our neck velocity and our airflow. So if I were to populate that with, say, 150 CFM, it'll calculate and change velocity, pressure, our throw distances. I'm just going to set this guy to 0. Bump him up to 500, and you can see static pressure changed, a calculated neck velocity of 636. So we're using 800 being pulled out of a table, but we're also taking that airflow and calculating from the neck size to give us an actual velocity. So when we're creating our parameters, we kind of want to chart out what information goes where. As I mentioned, where is it coming from, where is it going, and what's it going to do when it gets there. So we have our parameter where we've got our formula, our industry standard formula, and or a lookup table. And then we have controlling parameters. We have controlling parameters that will be bringing in information into those formulas. So we have additional parameters going into a formula that's going into that parameter that's going into our main parameter. Or we can have user input going into a controlling parameter that's then going into the formula and the parameter. So here's an example of using that. I'm going to look at breaker rating for an electrical connector. So if we take a look at that, we know all the parameters that go into this formula. We can either have a user input that uh, puts in the breaker rating manually. We can calculate it off of a horsepower value, or we can calculate it from MCA, FLA, KVA, or KW. We can use all of those in a single formula to help us calculate our breaker rating for essentially free. And then each of those have their own formulas and or user inputs. So when I'm building my family, I will actually chart this out and figure out which parameters need to go where, which formulas am I going to use, which values am I going to use. I can show you an example of the breaker rating for, say, an electrical connector. And this looks a little daunting, but it's really not. If you break it down into small parts, and also if you didn't notice, this is Notepad++, very handy program to use. If you're using long calculations, you go next to a parentheses and it'll automatically highlight the associated closing parenthesis. Super handy. So you can see in this first line, if we have the user input breaker rating is greater than 0, then it'll use that. And we use so we've got an override that we can put in, and that'll be the first thing that this parameter will look at. The control horsepower, if somebody puts in a horsepower or calculates a horsepower, it'll run out to a lookup table, find the breaker size, and look at the voltage column, and we're dividing by 1 to make it unitless so we can use it in our lookup table. And control horsepower again, and we'll also use the phase. So we're looking at voltage, horsepower, and phase to return an appropriate breaker size. After that, it'll start looking at the calculated value for MCA, and if it's less than 15, it's going to pop in 15. And same with as we go down that entire list. So I'll show you how that works. If we go into our family, and it's just a generic motor symbol with an extruded box, nothing fancy. And I've gone through and associated all the parameters. So we start off with power, balanced, number of poles, we link to the number of poles, and so on. And as we take a look at the calculations in here, up at the top I've got all my default inputs so that I can place, if I've got a spec sheet, I can fill in any one of these in order to have it populate. So it's all blank other than my voltage, power factor, phase, and number of poles. So if I put in, say, 15 horsepower, it'll go through and calculate all of the default values based upon the formulas that we have. So if I were to stretch this out a little bit, you could see control MCA is looking at the input MCA, and if it's greater than 0, then use it. But currently MCA is 0, so it moves on to the next one, looks at FLA, that's 0, so it'll move on. But if I did have something in FLA, it would multiply it by 1.25. After that, it goes into a lookup table to look at horsepower using voltage and phase. And then when we're done, we multiply it all by 1 amp to bring back our units to come up with, in this case, 57 3/4 amps. And you'll also notice our horsepower is just linked straight to horsepower. We can actually set this back to 0 and you'll see that that goes back to 0. Now if our spec sheet only had FLA, we can pop in say 20 full load amps and populates down here and moves on. Our MCA gets calculated based on that, our kVA, our kW, and then another parameter for FLA depending on how your schedule works. And you'll see down here our breaker rating is now 30. And that's all based upon this 25 amps. So if I go down to, say, 19 FLA, now it's going to be a 25 amp breaker. So we know what our industry calculations are. You know, we can use our kW and multiply that by power factor, or kVA, multiply that by our power factor to get our kWs. Now, some of the benefits that we have doing all this is that if I'm in my project and I've got some formulas or lookup tables associated to a family, you can see this is a 6-inch neck on my diffuser at 100 CFM. As I bump this up, that neck size will automatically change. And that information, that 200, goes into my ductwork. It's 200 CFM, and all of that gets summed up, coming back into a VAV, and in this case I'm using an electric reheat. And we can use that information. So I have, here we are, 1150 CFM coming in, which is, according to, we use the tightest catalog in this particular family, gives us a 12-inch inlet diameter. And you can also see I'm pulling more information on this family to populate a minimum airflow and a maximum airflow based upon that 12-inch neck size. We can also calculate BTUs based upon the CFM. So if our if our air terminals require more CFM, we can bump that up to 500, let's say. Take a look at it. Come down. Now our heating coil capacity has jumped up a couple thousand BTUs. So we can use this associated to an electrical connector, which is going to go back to its source and provide a load for our electrical designers. And if we go a little further, we'll see what our heating coil velocity is. Again, that's all just calculated based upon heating coil face area and the CFM being pushed through. We also have delta T connections, or delta T calculations. And our electric heating element power given to us in watts. And also, what do we need for a breaker on this particular piece of equipment? I can change this out from an electric reheat to hydronic, and we can get those same values. Let me scroll down to them here and give us our volume of the coil itself along with the velocity going through it. We have leaving temps, entering temps, dry bulb temps. What is the type of fluid that we're using? In this case, propylene glycol, fin density, and then calculated face velocity along with pressure ratings. So if we come down, here's our heating coil flow, and we can use this 0.9 GPM in this case on to help calculate the flow and size a pump accurately and size our system, whether we have expansion tanks or whatnot. If you recall, that's 12 inches. If I go back in and drop this down to, let's get 100 again, that next size goes back to 6. This one drops down to 10. Now, one of the other nice things about having all these parameters and calculated values is that within our workflow, if I have this particular space with 8,390 square feet, and I send this out to train trace, get my heating and cooling loads back, I know what my CFMs, my calculated CFM for the space is, I can quickly just take a look at, okay, I have a 300 CFM, 300 CFM, and 100. So we can come through and just quickly bump all these up. That's probably going to be 550, 550, 550, 550. And if we ever have a question on which one this is, we can highlight it and use show in model, but apparently I can't. So if I highlight, I'll just highlight this guy right here. Use Control Tab, back, and you'll see this air terminal, this guy, this one, and this one have all been changed to 550 CFM. And if we just select our system, we can quickly come in here and just say resize it. Are we going to do 1200 feet per minute and 0.08 friction or 0.1? We can also restrict our size. We can say calculated size, or we can restrict the height and width or diameter. We can say OK, have it all calculated for us. You'll see that changed up to 19 inches diameter. And, now if we select our VAV, you can see that is getting all of our information pushed to it based upon 2200 CFM. If we go back to our thing, you can see actual is 330. I think I have one additional element in the system out here, which I think is 50. Yep. So back to the PowerPoint, if we can utilize all of our information and plan all this out to pull data from other formulas and populate one individual one. So formulas can be used for arithmetic, algebra, geometry, and the conditional statements are typically if and or, not, and yes and no's. We can round our values up or down. Generally, if I get below half a GPM, I will force it to round up to a half a GPM. But also, the Revit formulas, there's a forum post out there, Revit formulas for everyday usage. Fantastic resource with some really good information on how to utilize any of the particular formulas. Some good examples in them. And the Revit help also has conditional statements and formulas. Quick note about lookup tables. In the past, we've only been able to use length as a value, but in more recent releases of Revit, we can now use numbers, and that allows us to, it really opened the door for use in a lot of areas. As you saw, we can pull in horsepower information, we can pull in breaker size information, whatever it is that you might want, as long as it can be used as a numerical value and then added, multiply it by 1 to get your units and add those back in and populate your values in your schedules. And I don't think we have enough time to go through lookup tables, but here's a quick lookup table example. Use your size lookup table and then the lookup table name, the parameter name, the name of the column that you're looking for, and then the default if no. So this is where they vary from or differ from a standard conditional statement. So the default is at the beginning rather than at the end. And column B, it'll always start in column B. Column A is completely ignored. So you can either put in a value for column B or you can put in a parameter name to take a look at values in column B. Same with C, D. You can keep going along the columns. It's just going to go in order. As you can see, column D, I'm using the divide by 1 to make it unitless, and then when we're all done, we multiply the whole works by 1, in this case, to get CFM.